Part B uses the same setup as Part A and asks us to design an amplifier with a gain of 10 and maximum output voltage amplitude. So beginning with the small signal model again, we drew the small signal model in Part A, and we used that to derive the gain equation. I've written the gain equation here again for reference. And we said that this equation is approximately equal to negative GM times RC. The reason for that is because we said RC is the dominant resistor in this parallel combination, which means that R out and 1 meg don't affect the gain. And then in the second part, we said that R pi was the dominant resistor, meaning that R1 and R2 don't affect the gain, and we also made R pi 10 times larger than our input resistance of 50 ohms, so that doesn't affect the gain either. So that gives us R pi over R pi, which is 1, and that's why we ended up with GM and RC. So using this gain equation, we're going to say that the gain, which is 10, equals negative GM times RC, and GM is IC over VT, so IC RC over VT equals 10, and VT is 0.026, so IC RC equals 0.26 volts to give us a gain of 10. Now, our input voltage is, well, our DC input voltage is 10 volts, and if we subtract the 0.26 volts that we dropped across RC, that gives us 9.74 volts, and that means that V out, the DC bias point of V out is 9.74 volts. Now we want the DC bias point to be a lot closer to 5 volts because the maximum, in order to do the maximum voltage amplitude, we need to be between 0 and 10 volts since we're inputting 10 volts. So 9.74 volts is not very close to the DC bias point of 5 volts that we're looking for. So how do we fix that? Well, we could increase the voltage drop across RC, but that will affect the gain, and we know that we want a gain of 10. So to solve this problem, we're going to add an RE. So we'll jump over to LT Spice and add a resistor on the emitter. Now that changes the gain equation. So we still want our gain to be 10, and that equals RC over 1 over GM plus RE, and we're going to make RE 10 times greater than 1 over GM so that we can neglect GM, and our gain will be RC over RE. So using this equation and with RE in our circuit, we're able to make IC/RC equal 5. And we can use these two equations to solve for our three unknowns of IC, RC, and RE. If we pick one of the values, so we're going to pick RE equals 100, and then use that to solve the other two. So RC equals 1K, and IC equals 5 milliamps. Now we're going to double check that we have satisfied our condition of RE being 10 times greater than 1 over GM, because otherwise we need to pick a different value for RE. So RE is 100, it's 10 times greater than 1 over GM. GM is IC over VT, so VT over IC. VT is 0.026, IC is 5 milliamps, so that's going to give us 5.2, and this is good, so we can use these values. So now we're going to come over to LT Spice and set RE as 100 and RC as 1K, and then for our input, our AC input voltage amplitude, we're going to evaluate that to figure out what will give us the maximum output voltage amplitude that we're looking for. So with an RE of 100, if IC is 1 milliamp, the current is the same across RE that it is across RC. So we do 5 milliamps times 100, and that gives us a voltage drop of 0.5 volts, and then we need to keep a voltage drop of 0.3 volts, at least 0.3 volts across the transistor in order to keep it inactive. So that's 0.8 volts. And that means that our maximum output voltage amplitude for Vout is 10 volts, since that's the top rail, minus 0.8 volts, since that's going to be our bottom rail, since we have to drop those voltages across everything below Vout. So that's going to give us 9.2 volts as our maximum possible voltage amplitude. So we're going to set our input to 0.46 volts, because with a gain of 10, that will give us 9.2 volts. Then we need to get our bias point correct using R1 and R2 so that we have 5 milliamps dropping across RC. So we'll sweep R2. Using our dot step param, we'll go from 800K to 1 meg. And we're using the DC op point in order to sweep that for the DC, in order to find the DC current. We do need to call it dot step param. Now we need a voltage, or we need a resistance much higher than 1 meg in order to get a current of 5 milliamps, and we don't want to use resistors that are higher than 1 meg, so we're going to set this one to 1 meg and sweep this one instead to something lower than 1 meg, because this analysis right here tells us that we want R2 to be larger than R1. So we still need to go smaller. And it's pretty close to 500. So we'll sweep from 500 to 510, and then we'll measure it. It looks like it's right there at 505K, because it's our 5 milliamps we're looking for. So we'll set this to 505K. And that looks really good. So we'll switch back over to our transient analysis. Now we want to measure V out. And our voltage amplitude right now is 8.3. So we want to increase that. We can increase that by decreasing RE. And then we want to see if we're clipping on the top or the bottom. We'll zoom in on our transient analysis a little bit just to see that better. Looks like we are clipping a little bit on the bottom. So now we want to raise our DC bias point so that we're not clipping on the bottom anymore, and we can do that either by increasing R1 or decreasing R2. So we'll increase R1. That'll allow us to increase our gain by decreasing RE a little more. And now we're clipping on the bottom again. Looks like we might be clipping on the top a little bit now. So we'll just increase RE a little again. Or we could have decreased R1 a little. There's a few different ways that you can solve some of these problems, where increasing R1 will increase our bias point, which will eventually make us clip at the top. Decreasing RE will increase our gain, which eventually will make us clip on the top and the bottom. But we just want to get a balance between these two and our input voltage to give us the maximum output voltage that we can get. And we're going to call this good. However, we want to double check a couple things real quick just to make sure. So the voltage drop across the transistor needs to be at least, or from the collector to the emitter of the transistor needs to be at least 0.3 volts in order to keep it inactive. So we can measure that by measuring the voltage at the top and the voltage at the bottom. And we're going to look at the smallest point here. I'm going to move this into the picture real quick, just so that when we zoom in we don't lose our cursors. Now we're going to look at the closest point and make sure that we keep our 0.3 volts that we need. I'm going to move one of the cursors to the other one. And then we're right about exactly at 0.3 volts, just like we're looking for. So if we get to a point where we have less than 0.3 volts here, then we can fix that by either decreasing the gain to raise this here, or increasing the bias point to raise this here, depending on how much room we have at the top to allow us to make that change. So we're good there. And the last thing we want to make sure is that our gain is still 10, like we're looking for. So with 0.46 volts as our input, we have an output of 8.84 volts, and that gives us a gain of about 9.6, which is within 10% of 10. So we're good to go there as well, and we'll call that our maximum output voltage amplitude at 8.84 volts.